Welcome to my first lecture on game theory. In this lecture, I'm going to give an introduction and explain some problems that are part of game theory. I won't give you any solutions, but further lessons will actually talk about different solution techniques. When you hear the name game theory, you might think of things like chess and poker and checkers, and that's part of it, but it's much more general than that. And I have a few definitions on this slide here. Game theory entails the application of mathematics to the study of strategic interactions between two or more rational agents in situations with clearly defined rules and outcomes. A rational agent is a decision-making entity, for example, a person, company, or software that aims to achieve optimal results based on given premises and information. So I have a few definitions here from one is from the Free Dictionary by Farlix. It says game theory, a mathematical method of decision making in which a competitive situation is analyzed to determine the optimal course of action for an interested party, often used in political, economic, and military planning, also called theory of games. Then we have another definition from Britannica, the encyclopedia. Game theory is the branch of applied mathematics that provides tools for analyzing situations in which parties, called players, make decisions that are interdependent. This interdependence causes each player to consider the other players' possible decisions or strategies in formulating their own strategy. A solution to a game describes the optimal decisions of the players who may have similar, opposed, or mixed interests and outcomes that may result from these decisions. So this all seems kind of abstract, but we're going to look at some examples that'll make it a little more concrete. So I promised examples, but I did want to do a few more definitions here. I'll read through them. They're all kind of similar, but hopefully you'll start to get the idea here. So strategy in like things like chess and other games is just sort of the tip of the iceberg, where it's more applicable in business and military strategy. So there's some very elaborate game development in these different fields. So let's look at a few more definitions here from the Merriam-Webster online dictionary. Game theory is the analysis of a situation involving conflicting interests in terms of gains and losses among opposing players. So this kind of gives the idea of some values, or it could be money, it could be other measures where you're trying to balance gains and losses. From Investopedia, game theory is a theoretical framework for conceiving social situations among competing players. In some respects, game theory is a science of strategy, or at least the optimal decision making of independent and competing actors in a strategic setting. Then one final definition here from the Stanford Encyclopedia of Philosophy. Game theory is the study of ways in which interacting choices of economic agents produce outcomes with respect to the preferences or utilities of those agents, where the outcomes in question might have been intended by none of the agents. We'll see some examples of this. This may seem a bit vague here, but there are cases where each party kind of does what they think is the best things for themselves, and then it turns out they both lose out in the final analysis. So I have an example of that. Let's look at our first example, and this will come up a few times. It's a very popular example in game theory. So it's called the prisoner's dilemma, and there's different variations. I'll give you a couple variations as we go through the lesson. So two individuals, Mr. A and Ms. B, are accused of a serious crime, arrested and placed in prison while awaiting trial. Before initial questioning, The prisoners have no means of communicating with each other. The prosecutors lack sufficient evidence to convict the accused of a major charge, but they have enough to convict both on a lesser charge. Simultaneously, the prosecutors offer each prisoner a deal to basically betray the other and in return get a lesser sentence. So the idea is that if one betrays the other, then they could have a major charge against the other person. So these are the details of the game. And again, neither A nor B can talk to each other, and so they can only rely on the information they're given from the prosecutors. And if A and B betray each other, then they each get sentenced to 2 years in prison for the major charge, but a reduced sentence since they cooperated with the prosecution team. Okay, so that's the first condition. If one betrays the other and the other remains silent, the betrayer will get set free and the other will serve a 3-year prison term for the major charge. If both remain silent, each will serve 1 year in prison. Okay, so let's summarize this on the next slide. We have a way of doing this, which I'll show you in a second. The information that we talked about on the previous slide is summarized in this table here. It's known as a payoff matrix. And you can see here that we have A on this as the rows and B is the columns. Then the first entry represents the payoff for A, and the second entry represents the payoff for B. So if A and B both remain silent, they both get 1 year in prison. However, if A remains silent and B betrays A, then A gets 3 years in prison and B is set free. That's why there's a 0 here. And vice versa, if A betrays B but B remains silent, then A gets set free but B has 3 years in prison. And if they betray each other, then they both get 2 years in prison. So this is a symmetric game also. This entry here and this entry here are kind of the reverse of each other. This is known as the normal form of a game. For two-player games, the normal form of a game is typically represented as a matrix, as we've shown here. For games with 2 or more players, which is typical, but we'll usually stick with simpler examples just to make some points. The matrix representation is not used in that case when you have more than 2 players. In such cases, a game is represented by a function that maps each possible combination of strategies with an associated payoff for each player. And the other thing I wanted to mention, I didn't on the last slide, is that A and B both know what offer was made to the other party, so they can reason as to what they should do based on what they might think the other party would do. So we'll get into solutions later on in more detail, but I thought I'd give you a little bit of a preview here. So if we analyze this from the point of A, and A first looks at what should I do if B remains silent? And A sees that the better choice is to betray B because they would get set free as opposed to serving 1 year in prison. And then A says, well, what should I do if B betrays me? And if A remains silent, A gets 3 years in prison. And if A betrays B, A gets 2 years in prison. So for either choice by B, A would be better off in betraying B. And since this is symmetric, the same thing holds for B. B is better off betraying A. So logically, if each player, A and B in this game, analyzes what's the best choice for them, It's to betray the other. And so you end up with this solution here. They both get they both get 2 years in prison. However, you can see what happens is there's an unintentional effect because if they both do this, they miss out on this possibility here where they both could just get 1 year in prison if they both remain silent. So that's sort of the paradox of this game here. All right, so let's continue with our analysis. Here's a variation of our matrix. Sometimes you want to just have positive numbers, and you can do this by just adding the same number to all the different outcomes. So I did this by adding 4 to everything, and you can see you get 3, 3, 1, 4, 4, 1, and 2, 2. So that's just a variation on how you would represent the situation. This is more literal, I guess, because you have it actually represents the number of years in prison, or where 0 is you get set free. Then here is not as clear as to how this maps to the statement of the problem. But the advantage is you have all positive numbers now in this form. So they're equivalent, and you would come to the same conclusion using the analysis that we did before, that 2, 2 would be the selected solution from A and B, but they would miss out on getting a higher payoff here. What we just saw in terms of the prisoner problem or game was a simultaneous game. Both parties made their decision independent of each other, not knowing what the other party had decided. There's also sequential games that go back and forth where one party sees what the other party or parties has done, and then that party makes a decision and it continues. So, for example, Go, chess, checkers, tic-tac-toe would be sequential games. I have an example here. Let me point to it. We have 2 people. Aristotle wants to sell his laptop computer to Bernice. Assume that he's considering 3 prices, $1, $2, and $3,000. Bernice can either accept or reject the offer from Aristotle. Aristotle makes his offer first, and Bernice decides. So it's basically a sequence. It's just 2 steps, but it's still a sequential game. Bernice values Aristotle's computer at $2,500. So, for example, if Aristotle offers the computer at $3,000, Bernice would perceive a loss of $500. So I have that shown here in this figure. It's known as an extensive form of a game, this representation. So you see Aristotle has the 3 choices. Then Bernice can either accept or reject. And these ordered pairs have the profit to either Aristotle first and then Bernice second. So this is the one we just talked about here. If Aristotle offered a 3,000 and Bernice accepted, that he would perceive a profit or a payoff of 3, and Bernice would see this as a negative 500, or what I represented here as minus 0.5. If she rejects in any of these 3 cases, it's 0 and 0, and neither side gains or loses. In the second case, if Aristotle offers it at 2,000, then he would have a profit of 2 or a payoff of 2, and Bernice would see it as a profit or an advantage of 0.5 or $500. And then in this last case, Aristotle would see a profit or payoff of 1, and Bernice would see an effective profit of 1.5. So we're going to get to solutions later in another lesson, but I'm tempted not to just leave you here hanging in terms of what would happen if each player followed logically. So we start from the bottom in this analysis, and we see what, maybe I should point to or circle this. In the first case here, Bernice has to choose between these 2, So this is a negative and this is a plus, so she would select this one. Then in the second case, this would be 0.5 versus 0, so she would go for the 0.5. And then in the last one, it would be 1.5 payoff for Bernice versus 0. So again, she would go here, maybe go with green. So Aristotle knows this. So he would only look at these three here, knowing that these are what choices Bernice would make in the three cases that he has available to him. So if he's looking at either 0, 2, or 1 in terms of his payoff, so he would go with the highest one, and that would be here. So this is where the 2 would sync up, which you might intuitively think that's what would happen, that things kind of balance out here. Okay, so that's the general way you would solve this type of problem. You would work bottom up. There could be more layers, which makes things more complicated. This was just a two-step problem. So let's look at a variation of this on the next slide. On the previous slide, we used money as the criterion for the choices between Aristotle and Bernice, but it may be that Aristotle and Bernice are friends, and Aristotle doesn't want to overcharge Bernice. He doesn't want to lose money necessarily either, so his preference would be to go with 2,000 as his first choice. So we'll give that a payoff of 3, and then the second choice is 1,000. We'll give that a payoff of 2, and then the last choice for Aristotle is 3,000, excuse me, and we'll give that a payoff of 1. And we'll use 1, 3, and 2 as in the analysis rather than these dollar amounts. And let's say that Bernice has the same view. She doesn't want to take advantage of Aristotle. She wants to pay a fair price. So her payoffs, her perceived payoffs, are the same for the different prices here. So we can summarize that in a chart here. If Aristotle offers 3,000 or 1, this option 1, his least favorite option, then if Bernice accepts, they would both have a payoff of 1. She would get her least favorable option, as would Aristotle. And if she rejects, they would both have a wash, a payoff of 0. Then in the second case here, if Bernice accepts, they would both have an effective payoff of 3, since they view this $2,000 as the most favorable option. And if she rejects, again, it's 0 on both sides. And then on the third case here, if Bernice accepts, again, because both Bernice and Aristotle have the same value system in terms of payoffs, it would be 2 and 2, and then 0, 0 if they reject. So here it's even easier. We don't even need the analysis we did in the previous slide. We can just see that this makes the most sense for both, for Aristotle to offer it at 2,000 and for Bernice to accept at that price. And of course, there are many other things that might be important. It's not just money or some type of personal preference. There could be other factors, which we'll see as we look at more examples. In a symmetric game, the payoffs for playing a particular strategy depend only on the other strategies employed and not on who is playing them. In other words, if the identities of the players can be changed without changing the payoffs to the strategy, the game is symmetric. As I mentioned earlier, the prisoner's dilemma, as I first posed it, is a symmetric game. If for some reason the deal offered to Mr. A was 6 months for betrayal of Ms. B, 6 months or 0.5 years, while Ms. B remains silent, then the game would be asymmetric and have payoff matrix shown in the table below here. So this entry, this entry, and this entry were the same as before, but we just modified this. Instead of 0, we made it 0.5, and now these entries are no longer the same, and we have an asymmetric game. On this slide, I have another example, pitching pennies. You may have played this as a child. So one version is that you have two players, A and B, and one player wins if there's a match. So if there's two heads or two tails, then, for example, player A wins. And if they're opposite, one head and one tail, then player B wins. So the strategies, which we're kind of stretching the use of the word strategies here because it's probabilistic, but I've called them strategies, and I summarized it here in the table. So if there's A and B get heads, then the payoff is that A gets 1 penny and B loses 1 penny. And the same thing down here. If you have A and B both getting tails, A wins a penny and B loses a penny. And then you have the other two cases where you have heads for A, tails for B. So they're different. So A loses a penny and B wins a penny. And then the opposite of that is tails for A, heads for B, and you have A losing a penny and B winning a penny. So this is called a zero-sum game because each one of these payoffs adds up to 0. So whatever one player loses, the other player wins. You've probably heard that in general. The zero-sum game just means people involved. If you have two people involved, whatever one person loses, the other person wins, vice versa. Okay, and the prisoner's dilemma was not a zero-sum game. Both examples of that, or both versions of that, when you added each of the elements and the payoffs for each cell, you didn't get to 0. So that was not a zero-sum game. Okay, so that's a class of games that have certain types of properties and solutions. So we'll define this here, but we'll get into more details in later lectures on the topic. If we stay with the pitching pennies game, but we change the payoffs, and we add 2 to all the payoffs, which I've done here. So there's still a difference of 2 points in each one of these items here. So in a sense, the game is similar, but no longer do the 2 payoffs add to 0. So you have what's called a constant sum game. You notice everything here adds to 4. Each one of these 4 cells, if you add the 2 elements in each tuple, you get 4. So this is a variant of a zero-sum game. And I just made a note here. Clearly, the set of zero-sum games is a subset of the set of constant sum games, because in that case, it's summing to 0. Further, it is also possible to modify a constant sum game to get an equivalent zero-sum game and vice versa. So they're basically the same. Typically, people talk about zero-sum games, knowing that they can if they have a constant sum game, they can rearrange the payoffs just to get it in the sort of a standard format. So I have another example of a game. It's called rock, scissors, paper. And it's a game you normally would play multiple times. Children play this, maybe not so much now, since everyone has computers and laptops and cell phones. But before we had computers, children would play games like this. And the idea is you would kind of hold your hand behind your back, and you can either exhibit a fist, 2 fingers to represent a scissors, or an open hand to represent paper. And the fist would represent a rock. And then depending on what your opponent offered, you could determine whether you won or your opponent won. So I'll go through the different options. Rock beats scissors. So if you put out your fist and your opponent puts out 2 fingers, then the rock would win because rock dulls scissors. So you would get 1 point and your opponent would lose one. Then in the second case, you put out scissors and your opponent puts out an open hand for paper. Scissors cuts paper, so you would win 1 point and your opponent would lose 1 point in that case. And then the next case, if you put out your hand to represent paper and your opponent put a fist out, you would win again because paper wraps rock, and you would get 1 point and your opponent would lose 1 point. And if both you and your opponent do the same thing, both rock, both scissor, or both paper, then it would be a draw, and you would each get 0 points. So the trick is you want to do this quickly, so you don't want one player to see what the other player is offering and then change their hand position. So that leads to a lot of arguments, and someone might be really quick and notice a fist coming out and quickly put paper so they would win. So it's a bit of an imperfect game, but that's how it works. And then I summarized it here. So I have A, the different choices for A and the different choices for B. And if they both do the same thing, we have 0, 0 is the payoff. But if A offers rock, then that would win against scissors. So A would get 1 point and B would lose 1 point. And if B put out paper and A put out rock, then A would lose 1 point and B would win 1 point. And then the other options are listed here. If you have scissors for A, B would win, right? You could have minus 1 point for A and a plus 1 point for B. And if A put out scissors and B offered paper, scissors cuts paper, so A would win one and B would lose one, and so on, just following these rules here. So it's a zero-sum game the way it's set up. All of these each cell, the entry in each cell adds to 0. And again, this is a game that's typically played multiple times. You may want to keep score and see who has the most wins. It's similar to the penny game in that sense that the pitching penny game that you would play multiple times. Although this is not probabilistic. The penny game is, at least as presented, the penny game is probabilistic. This is the final slide in my first lesson on game theory. I'll have some more. If you like this, please give it a thumbs up and stay tuned for more lessons on this topic. So I have a few points here. For repeated games such as rock, scissors, paper, it would be unwise to keep playing the same strategy. You wouldn't want to keep doing rock, 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 because your opponent would catch on and then they would just keep doing paper and winning every round. So deterministically playing a given strategy is known as a pure strategy. And you may want to do that in some cases. If the game is such that you can always win, you would play the pure strategy, and your opponent would play a strategy that minimizes their loss, knowing that they can't win if you keep playing that winning strategy, but they might be able to minimize their losses. And then we have what's called a mixed strategy, and that's what you would do in the rock, scissors, paper. You would vary your selection between rock, scissors, and paper roughly 1/3 of the time, and you could somehow randomize it. I have one suggestion here where you might roll a die. If it's 1 or 2, you would try rock. If it was 3 or 4, you would offer scissors, and 5 or 6, you would offer paper. But there's other ways to randomizing it. But in fact, that is the best solution for each player to offer one rock, scissor, paper 1/3 of the time randomly. Then the pitching pennies is also a mixed strategy, although that's kind of built into the coin, since that gives you head or tail. Assuming it's a fair coin, you're going to get 50/50 chance of either getting the heads or a tail. Okay, so that was it for the first lesson. We'll get into more of the solutions in the second solution. They give you a few hints here in this lesson, but there's more details, especially when you get into these mixed strategies. You have to do a little bit of math. It's not that complicated, but you need to do a little bit of math to figure out what's the best mixed strategy, and then um, you can claim a solution to the problem in that case.